Any questions before we get started? Okay, so if not, then with this lecture, we're going to start on the fourth and sort of final module of CS261, which is about NP-hard problems. And pretty much all of CS161 and all of the first half of CS261 focus on problems that are solvable in polynomial time, right? That's kind of what you've been doing for like a quarter and a half, is learning polynomial time algorithms for lots of different problems. Now, unfortunately, it's kind of a sad fact that in practice, there's actually a lot of problems which are both important, practically relevant, and pretty frequently occurring, which we do not believe are polynomial time solvable. Okay, so they're NP hard, so unless P equals NP, there's no polynomial time algorithm for them. And so the question is, but just because a problem is NP hard, that doesn't mean you don't have to do your best to solve it. I mean, it may be some crucial optimization problem for your startup or whatever. So it's still important to kind of know what are the options you have available to yourself as an algorithm designer when a problem is NP hard. And so that's what we're going to focus on for the remaining lectures, and primarily we're going to focus on approximation algorithms. So I'm not really going to talk at all about NP completeness or NP hardness in this class. In 261, I sort of assume that you've seen that in previous classes, 154, or even before that. If you want sort of a refresher on NP completeness, how to define it, how to interpret it, I'll put some 161 level videos up on the course website if you're interested. Okay. All right. So what does it mean as an algorithm designer if your problem is NP hard? Well, I mean, one thing to remember is it's not a death sentence. It doesn't mean it's literally hopeless to do anything non-trivial for the problem. But it does kind of like throw the gauntlet to the algorithm designer. It kind of says like you're going to have to step up your game in various respects. So yeah, and particularly you have to make some kind of compromises, right? So maybe the compromise is, you work a lot harder, you spend a lot more time on the problem, you buy like thousands of cores. Maybe the compromise is you only restrict attention to kind of relatively modest size inputs. Or maybe the compromise is you sort of relax correctness and look at approximation. So those are the things we're going to be talking about. So possible compromises. Okay, so it's not a death sentence, but it does generally mean you need significantly more human and computational effort to get an acceptable solution to NP hard problems. Okay. And there is, of course, sort of a trade-off, sort of the more work, computational and sort of human thought you put into a problem, the better you expect to do. And so we're going to be exploring a continuum, like some things which are kind of quick and dirty, and maybe the results you get aren't that strong, and then if you work really hard, how do you get excellent results? So we'll talk about that whole continuum. All right, so the first thing you can do is you can try to make the problem go away. You can say, okay, well, maybe this problem in general is NP hard, but maybe my application has some special structure, and with this special structure, the special case of the NP hard problem is actually polynomial time solvable. Okay? And this happens a fair amount. In fact, you've already seen an example in this class. The vertex cover problem in general graphs is an NP complete problem, but as you saw in a problem set in bipartite graphs, the special bipartite case, vertex cover reduces just to max flow min cut, and it's polynomial time solvable. So sometimes when you do a restriction to a special case, you wind up in P. You wind up being poly time solvable, that's great. Sometimes you're still NP hard, but you're in a sense still much easier than where you started. We'll see an example for that when we talk about the traveling salesman problem next lecture. In any case, I do want to point out that, I mentioned that sort of doing well on NP hard problems takes not just computational, but human effort. And so, implementing this step definitely takes sort of domain expertise and human effort. You have to understand your application, you have to understand what special structure your application has, and then you have to figure out an algorithm which exploits that special structure, okay? But when it works, that's a great resolution. So you don't want to solve NP hard problems if all you really care about is a polytime special case. All right, so you can also spend exponential time on the problem, but hopefully still better than brute force. Okay, so sort of we sometimes almost identify NP-hard problems, which are those that seem to require brute force, but the real situation is actually a little more nuanced than that. There's a lot of NP-hard problems where, while we don't know any sub-exponential time algorithm, you can do better than brute force. So instead of brute force might be n factorial, and we know an algorithm which is 2 to the n. Or brute force might be 2 to the n, but we know an algorithm which is 1.5 to the n. Okay, so we don't know anything sub-exponential for any natural NP-complete problem, but sometimes there are significant shavings you can do with respect to just the most naive brute force search algorithm. Time permitting, we'll see a couple examples in 261, in traveling salesman problem, and in 3SAT as well. Okay. And I should say, pretty much in practice, right, there's almost no NP-hard problem you would actually resort to just brute force search. You would always try to do something smart. So in a class like 261, we sort of focus on, stuff that works fairly generally and that you can prove guarantees about. But in practice, keep in mind that, there's always heuristics which usually do at least some successful pruning, at least some successful speed up over brute force. Although in practice, those are often super application specific. And so for that reason, they don't really fit inside a course like 261, which is focused on general techniques. You can also say, well, maybe we want to be fast. We want to handle large input sizes. And so then a possible compromise is to relax correctness. So hopefully you relax it in some bounded way. Hopefully you're still in some sense approximately correct, at least on most of the instances, if not all of them. This is what we'll be mostly focusing on for these last 3 weeks. So what this is called when you relax correctness, at least for optimization problems, is approximation algorithms. Now, as you know, you can study approximation algorithms even for problems that are polynomial time solvable. So this particularly came up when we were discussing matching. So matching is polynomial time solvable, in the non-bipartite case even, but it's fairly slow, the exact algorithm. So in the problem set, you explored some ideas where you'd prove approximate, say, near optimal matchings that run in near linear time. Okay, so we've already seen approximation algorithms for problems in P, but for NP-hard problems, really, they take on a sort of new importance because polynomial time exact optimization just isn't an option. Okay. All right. So what's the game in approximation algorithms? So we're going to take as a hard constraint polytime. Okay. In the worst case, so in every single input, we want an algorithm that runs in polynomial time. Obviously, the smaller the polynomial, the better. But anything polynomial is a good start, much better than exponential brute force search. And then the goal, again, we're going to be talking always about optimization problems, so there'll be a notion of an optimal solution, and we just want to get as close to it as possible. Okay? Close in the sense of having objective function value close to the best possible objective function value of any feasible solution. Okay? So that's sort of at a high level of what approximation algorithms are about. You have an NP-hard problem, you can't solve it exactly in polynomial time, presumably, but if I give you a constraint of polynomial time, how close can you get? How close can you get to full optimality? And so there is now a massive, massive literature on approximation algorithms. A good chunk of the algorithms research world has been obsessed with approximation algorithms for basically 25 plus years now. So as a result, there's tons of results. There's a lot of sort of really cool general techniques. And so the goal in CS261 is just to expose you to sort of a couple of the ones that seem most broadly applicable, the ones that you might be most likely to remember later on. Okay, but just know there's a huge, huge literature on approximation algorithms. And I guess, sort of one takeaway, we'll do lots of specific examples, including in this lecture, but one just thing to keep in mind, what should be sort of cool for you, is that one thing approximation algorithm shows, it shows that literally every algorithm design paradigm that you've learned so far in your studies, which you've probably only used for exact algorithms, is actually again useful for the design of approximation algorithms. So greedy algorithms, divide and conquer algorithms, dynamic programming, linear programming, and then even some other techniques like local search, which are also useful for heuristics, all of those are used to successfully design good approximation algorithms. So we're almost going to be doing kind of a nostalgic tour of all the techniques you would have learned in 161 and seeing them useful now in this other context for NP-hard problems. Okay, so that's one thing to keep in mind. All right. So that's kind of, you know, the philosophical preamble I had for you. So let's do some examples. Okay, so what are some examples of NP-hard problems you might want to approximate, and how would you approximate them? So let me begin by just pointing out you actually already know several examples, really. Let me just remind you of some of the ones that you know. So first, a problem we studied exactly a week ago, min-makespan scheduling. Okay, so we were studying this at the time in the context of online algorithms. So the setting is you have m identical machines. There are n jobs each with a processing time, and the objective function is to minimize the makespan. What does that mean? That means you want the most heavily loaded machine to be as lightly loaded as possible. So you want to minimize the maximum load. Equivalently, we're basically trying to distribute the jobs as evenly as possible between the different machines. Okay? So that was the problem. We were studying it online where the jobs come one by one. But if you think about it, it's a totally reasonable problem to study offline. You could imagine cases where you actually know a whole batch of jobs that need to be scheduled. You know them at once. And then you want to do a more kind of centralized optimization to schedule them all in a smart way. So the offline problem also makes sense. Again, offline means you have all the jobs at the beginning. So that problem turns out to be NP-hard, okay, computing the schedule with the best possible makespan. We're not going to prove that, and really, we're not really going to prove any of these NP hardness results. I'm just going to state them. You really already know how these things are proved if you've taken, say, CS 154. Okay, so you take some known NP-complete problem like SAT, and then you reduce it to the problem that you're talking about, and that proves that it's NP-complete as well. So you should have seen a bunch of reductions of that form in your previous courses. All of these are proved by exactly those same kinds of reductions. Okay, and I'm not going to do it. Not going to do it here. All right, so for our purposes, let's take it as a fact that it's NP-hard, so we don't expect to get an exact solution in polynomial time. What would be a polynomial time algorithm that gets close to opt? Well, let's just revisit what we were thinking of at the time as our online algorithm, Graham's algorithm. And Graham's algorithm, in the parlance of approximation algorithms, is a 2 approximation. What does it mean that an algorithm is a 2 approximation? It means it runs in polynomial time. Okay, so remember what Graham's algorithm is. You go through the jobs in an arbitrary order, okay, one by one, and you always schedule the next job on the machine that has the lightest load. Clearly a polynomial time algorithm, okay? Moreover, we proved back then, that the schedule produced by Graham's algorithm has makespan at most twice the best possible in hindsight, okay? So the best possible in hindsight is the same thing as our optimum, right, for the offline problem. Okay, so now it's just that both the algorithm and the optimal solution have all the jobs up front. So because Graham's algorithm had a competitive ratio of 2, because it always produced a schedule no more than 2 worse than the best in hindsight, reinterpreting it as an approximation algorithm, we can call it a 2 approximation. Always output to schedule within factor 2 of the best possible. And this 2, this is usually called the approximation ratio of an algorithm. Okay, it plays exactly the same role as the competitive ratio for online algorithms. They just use a different word for it in the offline case. Okay? So, okay, so you could say, well, all right, so for Graham's algorithm, you know, if really what you care about is the offline problem, the fact that Graham's algorithm actually processes jobs online, that's just kind of a bonus. It wasn't really a constraint for the offline problem. So it's natural to ask, well, you know, maybe I can somehow do better if I have all of the jobs up front, okay? And you can, actually, for this problem. And actually, a very simple idea, which you'll explore in problem set 4, already proves this, which is before you do your single pass over the jobs, you just sort them. Okay? Process the biggest job first, then the next biggest job, ending with the smallest job. Now, if you think about it, sorting the jobs by processing time, that's definitely not an online computation, right? If I feed you the jobs one at a time and you have to schedule in that order, you can't sort. But if you have them all up front, you can sort them and then go in that order. That lets you beat the factor 2 actually by a significant amount, okay? So that's an example of, you know, how offline algorithms can do things that online algorithms cannot. Yeah, so P set 4. Can do better offline. Okay, so that's example 1. I want to go through sort of 2 more examples that just, to just reinterpret previous stuff you've seen as approximation algorithms, then we'll do a new example. So any questions so far? Okay. So, okay, example number 2. So this is something you may or may not have seen before. It sort of depends on who you took 161 from. I teach this when I teach 161. Some other people do too, but I know some people don't. So hopefully, though, you at least heard of the Knapsack problem, which is sort of a traditional killer app for dynamic programming. So what's the problem? So the input is n items. Each item has both a value and it has a size or a weight. And then you also give you a knapsack with some fixed capacity. And the goal is you want to pack the knapsack, you want to stuff it, subject to the capacity. So the sum of the sizes of the items you pick should be at most the capacity. Subject to that, you want the most valuable subset possible. Okay? So you pick the subset of items with maximum value that fits in this knapsack. And if you think about it, like, whenever you have like a single shared resource with bounded capacity, it's basically a knapsack problem. So it comes up all the time. Okay, so what do we know about knapsack? And again, so if you want a refresher, if you never saw that, I'm not going to teach it again in 261 because I teach it in 161, but I'll put some, again, some 161 level videos up on the course site if you want. But let me just sort of remind you of the executive summary. So first of all, like I said, the students usually learn this for dynamic programming. Okay, so you learn an exact dynamic programming algorithm that solves the knapsack problem. Now, one thing which is pretty confusing until you get used to it, so the knapsack problem is actually NP hard. Okay, so there's no polynomial time algorithm for the knapsack problem. Let's remember what polynomial time means for a second. Right, so polynomial always means polynomial in the input size. Okay. Now, if you just have a graph with like n nodes and m edges, it's clear what the input size is. It's like n plus m. But remember, there's a subtle point when the input has numbers, okay, like the weight of an edge, the capacity of an edge, or the value or the weight of an item in knapsack. Right? So if the weight of something is 1,000,000, what's the input size? Well, the input size is just how many keystrokes it takes to type in the input to feed it to a program. And you only need 7 keystrokes to type down the value of 1,000,000. Okay? So the input size is logarithmic in the magnitudes of the numbers. Okay? The input size is the number of digits needed to write down all of the numbers in your problem. Okay? So polynomial input size means polynomial in the number of objects plus the number of bits necessary to represent all the numbers. And the knapsack algorithm is not polynomial in that sense. Okay, so the typical running time for the knapsack dynamic programming algorithm would be n, the number of items, times, or let's say n squared, times the maximum item weight. Okay? So if I multiply all of the item weights by 10, this running time actually gets slower by a factor of 10, even though the input length only went up by a single digit per item. Okay? So that's called a pseudo-polynomial time algorithm, where it's polynomial in the number of objects and the magnitudes of the numbers rather than in the logarithm of the magnitudes of the numbers, rather than in the number of digits, okay? So that's how you reconcile the fact that knapsack is on the one hand NP hard. You cannot solve it exactly in time polynomial in the number of digits and the number of items, unless p equals np. On the other hand, there are, and again, this is an example of beating brute force search. Right, brute force search for knapsack would be 2 to the n, try all subsets of items, and this dynamic programming algorithm in kind of almost all cases of interest will be much faster than that brute force search algorithm. Okay, so this is an NP hard problem where you can really do something non-trivial. Okay, so that's what's up with solving knapsack exactly. So what if you really want to be in truly polynomial time? Okay, and you're willing to give up a little bit on correctness. So you can also, there's a very natural greedy algorithm where, the gist of it is you try to pack the items in order of what's called density, so the value per weight, bang per buck in a sense. So that will give you a 1/2 approximation, meaning it's guaranteed to output a feasible solution, total value at least 50% of the maximum possible. So that's the application of the greedy idea. So let's say dynamic programming equals exact. And then if you use dynamic programming in conjunction with truncation, What do we mean by truncation? Well, what's wrong with the old dynamic programming algorithm? If the numbers are too big, then it runs a long time. So what if I just like lop off all the low order bits of all of the numbers in the input? So that actually that old algorithm all of a sudden runs fast because the numbers have many fewer digits or much smaller numbers. So that's what I mean by truncation. You take the input numbers, you chop them, you sort of divide them all by 1,000,000, something like that, and then you run the dynamic programming algorithm and then you scale back. So if you do that in just the right way, you can actually get a 1 minus epsilon approximation for any epsilon you like in time that's polynomial in n and 1 over epsilon. Okay? So now we know we can't get a 1 minus epsilon approximation for epsilon equals 0 in polynomial time. But the point is you can get as close as you want. You can get 99% in polynomial time. Okay? It's just that as you get closer and closer to optimal, your running time is blowing up with a 1 over epsilon as part of it. Okay? So you can't go all the way to exact, but for any constant epsilon, you really can't get a 1 minus epsilon approximation for a knapsack. Okay? So that's sort of the happiest case imaginable. Okay, so if your problem's NP hard, this is about the best you could hope for. That you get arbitrarily close approximation. Many NP hard problems, this is not possible. Okay? All right, so any questions about any of that? Again, this is all stuff I cover in 161, and I'll put videos up on the website if you want to check them out later. So any questions? Okay. All right, so now let me revisit something definitely all of you have seen, because this is, again, something we talked about exactly 1 week ago in the context of online algorithms, the Steiner Tree problem. So again, let me just quickly remind you the setup. So the input is a graph, undirected, with edge costs for each edge. And one thing I asked you to think through last week on exercise set number 7 was why there's no loss of generality in restricting ourselves to the metric special case. What's the metric special case? It means the graph, first of all, is complete. Every edge is there. Second of all, the edges satisfy the triangle inequality. Okay, so the shortest path between 2 points is just the one-hop path between the 2 endpoints. Okay, so we'll use that again here. So without loss of generality, G is complete, and the triangle inequality holds. Okay? All right, and then the other part of the input were terminals. Okay, so let me call, as a set, I'll call them capital R. All right. So maybe we have T1, T2, T3, for example. Okay? All right. So, we studied this in an online context previously, where the graph is specified up front, and these terminals T1 through Tk come in online, one by one. And at each time, it had to make a decision. Oh, what's the goal? So the goal is to output a subgraph of G that spans all of the terminals, and subject to spanning all the terminals is as cheap as possible, minimum sum of edge costs. So in an online context, we studied a greedy algorithm, which just processes the terminals in whatever order they come. Okay, so in some arbitrary, adversarially chosen order. But again, just like with scheduling, this problem makes perfect sense also as an offline problem, where I give you not just the graph, but also all of the terminals up front. Okay, so just tell you, these are the 100 terminals. Connect them as cheaply as possible, please. Okay? So that's the offline Steiner Tree problem. This again is NP hard. Again, I'm not going to prove it. Pretty much all of the NP hardness results from today, I think, date back to the original paper on NP completeness, or rather on sort of the pervasiveness of NP completeness by Dick Karp in '72. So these are all sort of among the very first generation of NP hard problems. And we gave a greedy algorithm which was a 2 log k competitive, or in the current context, we would call it a 2 of log k approximation algorithm. Okay? So remember what that online greedy algorithm was. It effectively processes the terminals in an arbitrary order. Each iteration, it adds one new edge, connecting the new terminal to some previous terminal, and amongst all of the possibilities, it does the obvious thing, it picks the cheapest of those edges. Okay? So that was the online algorithm, and it was what we proved is that the solution it outputs is within 2 log k times the best possible solution in hindsight, i.e. the optimal solution of the offline version of the problem. Okay? So, in scheduling, I mentioned briefly that you could do better in the offline case. If I give you all the jobs in advance, you can sort. And so the question arises is, if we study Steiner Tree in the offline case, can we do better than log k? Okay, you can't do better than log k with an online algorithm, it turns out. But you can with an offline algorithm. And that's what I want to show you next. Okay? And the high-level idea of why you can do better is the same as before, which is if I give you all the terminals at once in advance, you can process them in whatever order you choose. Okay? Not just in some arbitrary one that comes in one by one online. So, and again, we kind of want to sort of be greedy in some sense. So, okay, we're going to process the terminals one at a time. What's the best order for us? Well, probably the first thing you might think of would be, okay, among all the terminals that we might connect next, let's connect the one that we can connect as cheaper than any of the rest of them. Okay, so if there's 3 terminals left, we can pick any of them next. The first one has the shortest edge of length 3 to a previous terminal. The second one has the shortest edge of length 5 to a previous terminal. And the third one has a shortest edge of length 7 to a previous terminal. We'd pick the first one. We'd say, oh, let's go for the 3. Maybe after we include the 3, we'll be able to connect those other 2 cheaper than we could before. Okay? So that's an idea. So do the same thing as in the online algorithm setting, except process the terminals in a greedy ordering in order of, so basically at all times picking the terminal that you can connect as cheaply as possible. If you think about it a little bit, you realize that what this algorithm actually is? This algorithm is actually, what it's literally doing is just running Prim's minimum spanning tree algorithm on the subgraph induced by the terminals, it turns out. So if you go back and reread Prim's algorithm, what happens? You start from a node, you add one edge every time. Which edge do you add? You add the edge which is cheapest, and we'll extend the tree by 1. And that's exactly what this idea is doing here. So it's literally just computing Prim's algorithm on the subgraph induced by the terminals. So this is why it's called the MST heuristic. So in general, we can describe this offline algorithm as just output a minimum spanning tree of R, where R is the set of terminals. Okay? So you have n vertices, some k of them are terminals. You forget about the n minus k, you just delete the n minus k vertices which are not terminals. You have a graph on k vertices left. You compute an MST on that graph of k vertices. Okay? Certainly a polynomial time algorithm. Okay? Certainly outputs a feasible solution. Outputs a subgraph spanning all the terminals. Not totally obvious how good it is. Okay? Okay. And actually, it's easy to see from an example that it's not always going to be optimal. I mean, in some sense, we know that because it's an NP-hard problem. It's a polynomial time algorithm. But it's always good to see the concrete examples where they're not optimal. So here's I've redrawn an example from a week ago. This network here, which is complete and does satisfy the triangle inequality. So the greedy algorithm deletes, so remember the middle node is not a terminal, so the greedy algorithm will delete this, be left with a triangle, and compute an MST of the triangle. So that'll be something like this, the blue solution. So that'll have cost 4. On the other hand, the optimal solution will make use of the center spoke and achieve 3. Okay? So what's really tricky about the Steiner Tree problem is sort of adding extra vertices to your solution can actually allow you to have a cheaper tree. Because these vertices can kind of serve as rendezvous points that are kind of efficient for many terminals simultaneously. So that's what makes the Steiner Tree problem hard. And that's why this MST heuristic isn't always going to be optimal. If you just generalize this argument, you use sort of bigger and bigger wheel graphs, you can show that the ratio between the MST and the optimal solution can become arbitrarily close to 2. Okay? So you can amplify this example and make this gap bigger, make this gap around 2. And so then, and that's going to be tight in the following sense. The cost of the MST of R is at most twice the cost of the optimal Steiner tree. Okay? So in other words, the MST heuristic is a 2 approximation algorithm for the offline Steiner tree problem. Okay? Obviously blowing away the log k approximation we get from greedy, except for super small k. Okay? All right. Any questions? Other than how to prove the theorem? It's actually quite easy. So as far as announcements, problem set 3 is due tonight, as I'm sure you know. Problem set 4 I'll post as soon as I can, tomorrow morning at the latest. And homework 2 solutions are available at the front, and you should have your grades for problem set 2 already. All right, so any questions before we prove that the MST is almost twice as expensive as the optimal Steiner tree? Okay, well this is going to look a lot like our proof of the O of log k competitive ratio for the online algorithm, but happily it's actually going to be easier. Okay, so we'll use the same ideas, but we don't have to work as hard. And the reason is it's sort of easier to relate the cost incurred by the algorithm with the optimal solution in this offline case. We can do the whole thing in one shot rather than argue separately for each edge of the greedy algorithm, which is what we had to do in the online case. All right, so let T star be the optimal Steiner tree. So the following maneuvers should be familiar to you. So we again want to use the metric special case, the assumption that the edge have satisfy the triangle inequality. Why is the triangle inequality useful? It allows you to shortcut. Okay. So what do we want to shortcut? We want to shortcut something which includes in particular all of the terminals, and we want it to be cheap. How do we make sure it's cheap? We start with opt. What's the problem with opt? The problem with opt is it's not Eulerian, it's just some tree. So it's going to have degrees with odd nodes. But if we double every edge of the optimal solution, we definitely get an Eulerian graph because it doubles the vertex of doubles the degree of every vertex, and it only doubles the cost. Why is it nice to have an Eulerian graph? Well, because then we can take an Euler Tor, which uses every edge every once and visits every terminal at least once. Then we can shortcut, and then we can compare it to our MST, and we'll be done. Okay? So in detail, let H be double all the edges of T star. So we just take T star, and for each edge, we just make 2 copies. Both copies have the same cost as the original edge. Again, clearly Eulerian. All the degrees are even, which means it has an Euler Tor. We should also keep track of the cost here. All right, so T star has cost opt. So if we double every edge, all of H combined has cost exactly 2 opt. Now an Euler Tor uses each edge of H exactly once. So the total cost of all the edges on C is also going to be exactly 2 opt. Now as let me shortcut. So shortcut to a simple cycle on the full set of K terminals, T1 through Tk. Okay? So because T star, because it's feasible, spans all the terminals, which means that this Euler Tor visits every terminal at least once, which means it's well defined to say shortcut it down to a simple cycle on the terminals. Basically, you just look at the Tor, you look at the first occurrence of each of the K terminals, and then you just shortcut accordingly. Okay? Because the triangle inequality holds, shortcutting can only make things cheaper. So this is the most 2 opt. So now what do? Well, actually now, unlike the online case, now we're actually just sort of almost immediately done. So we have a cheap, simple cycle on the terminals. What do we have going for us in our algorithm? Well, the algorithm computed the MST, okay, the best spanning tree, spanning the terminals. We have a cheap cycle spanning the terminals. Pretty easy to turn that cycle into a tree. Just delete any edge of the cycle and you get a spanning tree of the terminals. And we picked the minimum spanning tree, so our algorithm's just doing better than that. Okay? So R minus an edge is a spanning tree. Since the cycle had cost the most 2 opt, deleting an edge also has cost the most 2 opt. Costs are non-negative. And MST, which is the output of our algorithm, is only better. And that's the full proof. So again, the spanning tree is again at most 2 opt. So any questions about that? Okay. Example number 4. So this one will be new to many of you, although it's totally fundamental. Again, I suspect this was one of Karp's original list of NP-hard problems. Set coverage. So what's the input? So the input is a bunch of subsets. Okay? So maybe there's a subset, there's another subset, there's another subset, and there's a subset. All of some ground set U. Okay? So subsets S1 up to SM belonging to a ground set U. Think of each set as just subset is specified by a list of its elements. Okay? So if it has 12 elements, it's just like a linked list of 12 elements in the input. And you're given a budget, K. And what you want to do is you want to pick K subsets, K of the given subsets, to cover as much ground as you can, okay, to maximize the area of your chosen sets in this picture. So goal, pick K subsets to maximize the size of their union. Okay? So it's clear what the problem definition is? So the thing to notice about it is, you know, so you want to maximize the size of their union. So obviously, all else being bigger, all else being equal, bigger sets are better sets. You want to cover more stuff. But it's not so simple, right? So if all the sets were disjoint, that would be fine. You'd literally just take the K biggest sets. But there's overlaps. So just because a set is big doesn't necessarily mean it's all that useful to you. It could be mostly redundant. Like in this picture, right, if you look at the 2 biggest sets, they have an enormous common intersection. So if you pick one of these 2 super big sets, then as a second set, you might do much better for yourself picking one of these 2 sets as opposed to the largely redundant big set. So it's these overlaps, this redundancy, which is what makes the set coverage problem kind of tricky. Okay, so you want big sets, but you also want small overlaps. Okay, so you know, it's like any sort of super basic problem. This shows up all the time. And in fact, usually problems come up sort of like thinly disguised and you need some sort of practice to recognize them. Set coverage, honestly, this just comes up like literally, basically, right? So for example, you know, maybe your startup has the funds to hire like K new people, okay? How do you associate a set with a potential employee? It just corresponds to the skills of that employee or the tasks that they could accomplish, if you like. You can hire K people, you want to cover as much territory as you can, have as many skills as you can get. Or maybe you're building things. You're building factories, fire stations, artisanal chocolate shops, whatever, and you want to cover as many neighborhoods as possible. Okay? Again, it's literally a set coverage problem. In machine learning, maybe you want to just identify a small number of features that explains as much as your data as possible. It's a set coverage problem. Maybe in HCI, you're trying to figure out how to display stuff on a screen, and the user only has a budget of like 3 or 4 menus or windows or whatever, and you want to figure out which 3 or 4 things should you display to maximize either, maybe the number of topics covered on an aggregator, or maybe the amount of functionality that the user can do with that set of menus. Okay? So really kind of all the time. All right, so yet again, NP hard. So we need to figure out what we want to do with it. And both in theory and in practice, a pretty good way to deal with set coverage is a greedy approach. This is going to be sort of one of the killer apps of the greedy design paradigm in approximation algorithms. All right. So what would be the greedy algorithm? We're going to pick sets one at a time. What's the first set? First set's going to be the biggest set. Why not? Right? Cover as much stuff as we can. How about the second one? Well, we could pick the second biggest set, but we kind of don't really want to count the elements already covered by the first set. So it's almost like we want to redefine the size of sets in our head after deleting out everything that we've already covered. And then with respect to that new measure, we want to pick the biggest set. Okay? So a little more formally, you just pick the sets one at a time, and in the ith iteration, you pick the subset that maximizes the number of elements that are newly covered. Okay? With respect to A1 through A1 through AI minus 1. And then you just return the case sets that you picked. Okay. Is everything clear? All right. Do I want these? Yeah, I do. So how well does it work? That's the obvious question. Clearly polynomial time, we're not worried about that. How well does it work? And it seems like a pretty good idea, actually. Kind of feels like it should work well. Okay, we know it's not going to be optimal, though. Right, because it's an NP hard problem. And so as usual, it's kind of helpful to kind of see what can go wrong. Some concrete examples where greedy is not optimal. So let's do some examples. So example 1. This will just be with k equal 2. Remember, k is the number of subsets you get to pick. So here, I'm going to do the following. So here's our ground set, U. And what I have in mind for being the optimal solution is that there are these two disjoint sets, S1 and S2, each of which is exactly half the ground set. Okay, so it's a partition of the ground set into S1 and S2, equal size. All right. Now, if this was the whole input, the greedy algorithm would have no trouble. It would just solve it optimally. So we need to trick the greedy algorithm into doing something wrong. Doing something wrong means it's choosing a set other than these two. But it's a greedy algorithm, so to get it to choose a set other than these two, we need to feed it a set that has 51% of the universe in it. Right? Otherwise, it'll take one of these, because they cover 50%. So that's what we do. We define an S3, which is 50 plus epsilon % of the universe. Okay? And that's it. So that's the whole instance. So what happens, well, the greedy is tricked into picking S3 first, right? Because that's the biggest of the sets. And now in the second step, it has to pick either S1 or S2. It doesn't matter which one it picks. Maybe it picks, for example, S2. Okay? And so what we find is that the opt is the full set of the universe, and greedy is roughly 3/4 of the universe size. Okay? Everyone clear on that? All right, so that's a concrete example of what can go wrong for greedy, proof that it's non-general optimal, which of course we already knew, but it's good to see this. Let's look at another example. Let's try to build on this idea. Now with k equal 3, okay? So what's opt going to look like? So it's 3 sets. So I guess instead of partitioning the ground set into 2 equal size sets, I'm going to partition it into 3 equal size sets. Equal size sets, yeah. Okay. S1, S2, S3. Each exactly 1/3 of the universe size. So again, we want to trick the greedy solution into making a mistake, into picking something other than S1, S2, or S3. And actually, we don't have to work quite as hard to trick it in the first iteration. These are 33% of the universe size, so if we just have something S4, which is 1/3 plus epsilon, then greedy will pick that in the first iteration. Now, we don't want the greedy algorithm, if we're sort of trying to have a bad input, we're trying to trick the greedy algorithm into still, even in the next iteration, even for the second set, it's still not going to pick S1, S2, or S3. Okay? So how do we make sure? So we got to feed it basically a set which is bigger than S1, S2, or S3. Well, not quite, because greedy is only looking at the newly covered elements. Okay? So we have to feed it something that's a little bit bigger than the sort of version territory in any of S1, S2, or S3. Okay? So suppose the greedy algorithm picks set S1. Okay? What would be the benefit to it? Right? So notice that each of these columns is 1/3 of the rectangle, and this is also about 1/3 of the rectangle. So in the intersection, one of these small squares, that's 1/9 of the universe. Okay? We have 1/9 in here. We have 2/9 currently in each of S1 and S2 and S3, relative to the elements already covered in the first iteration by greedy. So to fool greedy a second time, we just need to give it a set which covers slightly more than a 2/9 fraction of the universe. So that's easy to do. We just give it an S5 here, which is 2/9 plus epsilon fraction of the universe size. Greedy will then pick S5. And now in the last iteration, we allow greedy to pick S1, S2, or S3. And it doesn't matter which one. Okay? So again, maybe it picks S3. So again, opt is 100%. So what is greedy? So greedy is everything but these 2 squares. All right, so what's one of these squares? Well, this was 2/9 of the full rectangle, and then this is 2/9 of the subrectangle. So what is uncovered up here is 2/9 squared. Sorry, not 2/9 squared. 2/9 times 1/3, excuse me. So, yeah, anyway, so 1 minus 2 times 2/9 times 1/3. Right, so this is the 1/3 part, and this is the 2/9 part. So that's what's left uncovered by greedy, and that happens twice, both here and here. So this gives us 2/27, 4/27, shoot, this is wrong. Let me think. I see, this is a 4. Sorry about that. 1 minus 8/27, which equals 19/27. Okay? So again, so where does the third comes from? The third just comes from, I'm focusing on a column. Where does the 4/9 come from? Well, this is covering 1/3 of the column. This is covering another 2/9 of the column. So it's 5/9, leaving 4/9 of the column. Okay, so the width is 1/3 and the height is 4/9, and we have 2 such rectangles. Those are uncovered, so this is what is covered. Okay. What is this? This is roughly 70%. Okay, so why did I walk you through this? A couple reasons, but the first thing to notice is that by bumping k up from 2 to 3, we were actually able to get a bigger gap. Okay, the first example only showed greedy cannot be better than a 3/4 approximation. Now we know it actually can't be better than a 19/27 approximation. Okay? Any questions about the example? Examples? Okay, so you can extend this idea so using exactly the same pattern, and you can prove a lower bound on how good greedy could be for all k. And you get the greedy is no better than 1 minus 1 over k to the k. Right, so plug in 2. Right, if you plug in 2, this is a half, so this is a 1/4, so this is 3/4. So that's what we had here. Plug in k equal 3, what do you get? You get 2/3 raised to the cubed, so that's 8/27. 1 minus 8/27 is 19/27. So those are the k equal 2 and k equal 3 cases. Extending this idea, you get this expression for all k, for any k. Now maybe you're wondering, okay, well, like, what is this number? So it keeps getting smaller with each value of k, so it's decreasing. What is it converging to? Well, as k gets large, 1 minus 1 over k is very well approximated by e to the minus 1 over k. Recall that we had this figure. This was in the middle of the analysis of the multiplicative weights algorithm is when we were using this. That the exponential function is well approximated by 1 plus x, especially right around here, right around 0. Okay? So that means as k gets large, this becomes very close to e to the minus k. E to the minus k to the k, that's just 1 over e. So we're actually getting the same thing we had last lecture, 1 minus 1 over e. 63.2% roughly. Okay? So before this class, 1 minus 1 over e probably struck you as a weird number. Comes up surprisingly often, actually. Okay? So again, what was the point of all this? The point was as k grows large, if we don't restrict k to be small, then we're not going to prove a bound better than 1 minus 1 over e for the greedy algorithm. Okay, but of course, whatever, these are just our first examples. For all we know, there are much worse examples. But there aren't. So theorem. For all k, greedy is in fact a 1 minus 1 over k to the k approximation. And so in particular, it's always a 1 minus 1 over e approximation, and then it's better if k is small. Okay? So this is literally the worst example you will ever see when k equals 2. This is literally the worst example you'll ever see when k equals 3, and so on. Okay? So the next goal is to prove this. Any questions for that? Everyone clear on the problem, the algorithm, the statement, the tightness? Good. All right, so quick little lemma. So the lemma really is where we isolate what's special about the greedy algorithm, and then the proof is just going to be kind of a little algebra on top of that. So what's the lemma? pause the greedy algorithm in some iteration. Okay, I don't care which one. Suppose that at the moment, the current greedy solution, the I sets it's chosen so far, covers L elements. Okay, and I don't care what L is. Then, the next set chosen by greedy covers at least 1 over k opt minus L new elements. Okay. So what's the point of this lemma? So, in general, how do you prove good things about greedy algorithms? One of the most natural ways to do it is to kind of say every iteration of the greedy algorithm, something good happens. Right? And you saw this all the way back in like Dijkstra's algorithm, where you proceed by induction on the number of iterations, and you say every iteration of Dijkstra, it's correctly computing some shortest path. And so when it processes all the vertices, it's done, and it's optimal. Here we're not going to be optimal, we're going to be approximately optimal, but this is giving us a lower bound on the progress of the greedy solution relative to kind of how many elements it's currently missing. Okay? So if L is close to opt, we're already done. If L is far from opt, then this guarantees us a lower bound on how many new elements we get at the next iteration. So as long as we're covering much fewer than opt, we're going to make rapid progress in increasing. Okay? Which sounds like a good thing. It sounds like probably we should be home free. And we are, modulo little algebra. Okay? I guess I should prove the lemma for you. Do you see the proof of the lemma? It's kind of a one-liner, actually. Here's one way to think about it. Granted, at the moment we're only picking one set. But suppose we actually picked k sets right now. Should be kind of ridiculous, but suppose we did it. And actually suppose we just magically knew what the optimal sets were and we picked those k optimal sets. How many newly covered elements would there be, at least? How many elements would be covered, at least, if we picked all k of opt sets right now? Opt, right? We'd at least get the elements in those sets, right? So we'd boost our value up to opt from the current value of L, all right? So if we picked all k sets in the optimal solution at once, we would certainly boost our objective function by opt minus L. Now, these are k sets. And we're only picking one set. But if picking k sets would boost it by opt minus L, then an average one of those k sets would boost it by opt minus L over k. And so in particular, the most useful of those k sets would cover at least opt minus L over k new elements. Now we still don't know which set that is, but we pick the set in the greedy algorithm that maximizes the number of newly covered elements, so we only do at least as well as this best of the k optimal sets. Okay? So that's the proof. So it holds for one of the k sets in opt. Again, it even holds sort of on average for the sets in opt, and of course the max is always at least the average. And our set, greedy, only does better. Okay? So any questions about that? That's the lemma. So we're just a little bit of algebra away from the theorem now. It can be instructive to instantiate that lemma on our bad examples. So say k equals 2. What the lemma asserts, it says, well, okay, in the first iteration, L is 0, okay? K is 2. So the lemma is just telling us that whatever the greedy picks in the first iteration, it's got to be at least half the universe. Why? Because one of opt's Right? So if opt covers the whole universe, one of its sets covers half the universe. And indeed, S3 covers half the universe. Now in the next iteration, what does the lemma assert? It says, well, now the number of uncovered elements is opt over 2. And so it says we get at least 1/2 times opt over 2. So opt over 4, or 25%. And indeed, that's exactly what happened when we pick S2. The number of newly uncovered elements, covered elements, is a quarter of the universe size. So, not surprisingly, given that I've told you that the upper and lower bounds are going to match, that lemma actually is holding with equality in every single iteration in our bad examples. Okay? All right, so proof of the theorem. All we're going to do is iterate this lemma and see what we get. Okay? So let GK, or let GI denote the value of greedy after I iterations. By value of greedy, I just mean the size of the union of the I sets that it's picked so far. Okay? So we're going to try to understand how rapidly this grows. And again, the lemma sort of tells us that either you're already close to opt or GI, or you're going to get a big jump from GI to GI plus 1. Okay, so then, so GK is what we really care about, right? This is the final value of the final greedy solution. Okay, GK. So let's apply the lemma. So how many elements have we covered at the end? Well, it's however many we covered after k minus 1 iterations, plus the number of newly covered stuff in the last iteration, the kth iteration. How much did we cover in the kth iteration? Well, we don't really know, but we know it was at least 1 over k times opt minus L. L conveniently is just GK minus 1. Okay? So this is using the lemma. Okay? Also known as opt over k plus 1 minus 1 over k GK minus 1. Okay? Just reorganizing terms. And now, of course, we can just play exactly the same trick, right? So this gave us a lower bound on GK. GK minus 1, we're going to get exactly the same lower bound with the indices dropped by 1, okay? So at least GK minus 2 plus 1 minus 1 over K. Let's see. I see. I'm getting ahead of myself. Okay. Plus 1 over K opt minus GK minus 2. Okay. So this is just applying the lemma to GK minus 1. How many elements are covered? Well, it's whatever you were covering the previous iteration plus the newly covered elements in this iteration, and that, by the lemma, is guaranteed to be at least 1 over K opt minus the amount of stuff you were covering before this iteration. Okay? Now, if we want to substitute the blue thing back into this expression, just notice that this is all multiplied by a 1 minus K. So basically, every time we apply the lemma, we pick up another 1 minus 1 over K power on the remaining terms. So let me just rewrite this a little bit so it's clearer. So opt over K plus 1 minus 1 over K, opt over K. That is, plus, maybe I'll just skip to the end, skip to the punchline. Okay, so when you iterate, what do you get? You get at least opt over k plus opt over k 1 minus 1 over k plus opt over k 1 minus 1 over k squared, and so on. And you have one of these terms for each iteration of the greedy algorithm. There were k iterations of the greedy algorithm. The exponent starts at 0, so the last exponent is going to be k minus 1. Okay. This may be clearer if I also just write this as equal opt over k plus 1 minus 1 over k g k minus 2. Okay? So this term corresponds to this term, this opt over k. This opt over k times 1 minus 1 over k, that corresponds to this opt over k multiplied by that leading term, and then so on. Okay, and then we just keep iterating. So every time you apply the lemma, you get another term opt over k, but the 1 minus k is raised to another power. Okay. All right. So obviously, so this is something we know what to do with, right? So again, we just analyzed greedy iteration by iteration. We had this simple lemma, which sort of gave us a lower bound on progress. And happily, when all the dust settles, we just have a geometric series. We know what to do with geometric series. We know closed forms for them, right? So we bring the opt over k out front. So now we're summing 1 minus 1 over k to the I, from I equals 0 to k minus 1. So what do you get? So geometric series. So remember, it's a bunch of things of the form p to the I. You get a 1 minus p in the denominator. In the numerator, if you do the infinite series, then you just get 1. But so we have a truncated series, the last term is k minus 1, so we're going to have an error term in the numerator. So this is like the 1 minus p factor you should be used to from geometric series of p to the I. And then up here, what's the correction term? 1 minus 1 over k to the k. Okay? And so again, this is in your 103 notes, I'm sure. Okay? That's what you get with a geometric series. This notice is 1 over k. So that cancels out the k. Leaving us with opt 1 minus 1 over k raised to the k, as claimed. Okay? So that's set coverage in the greedy algorithm. Now, of course, this is a tight analysis. We know you can't do anything, you can't prove anything better for the greedy algorithm. We have bad examples. You might, of course, wonder, could you have a smarter algorithm? I mean, this is one of the most natural things you could try. And so this becomes sort of more amazing when you find out that actually, unless p equals np, there's no better approximation algorithm. So one can prove that any improvement over 1 minus 1 over e, or really sort of above this for any k, or for large enough k, would imply p equal np, okay, if you could beat that factor. So unlike the knapsack problem, where you can get 1 minus epsilon for epsilon as small as you want, here there's really kind of a hard barrier with how closely you can approximate set coverage, at least in the worst case in polynomial time. And that threshold is exactly 1 minus 1 over e, and it's exactly the greedy algorithm that gives the optimal approximation algorithm in terms of the worst case approximation ratio. So any questions about that? Okay, so that's the last real proof that I have for you for the lecture, but I do want to tell you just sort of about where kind of this idea has gone viral recently. So I'll say a little bit, just informally, about the problem of influence maximization. So it's funny because, this greedy algorithm was around in the 70s in the analysis. Actually, lots of generalizations. All that stuff was known in the 70s. The hardness result is more recent, more like the 90s. But so people knew about these greedy algorithms forever, and they've really just in the last 5 to 10 years totally gone viral in both machine learning and data mining. Okay, there's really lots of papers that think about these influence maximization problems and use these kinds of greedy algorithms, and you'll see 1 minus 1 over E in the papers and all this kind of stuff. So I want to just give you a little bit of a glimpse of this. So there's a lot, people have been looking at a lot of applications, but let me just single out one which is representative and has been particularly influential. So suppose you have a social network, by which I just mean a graph. And let's work with directed graphs. So you can think about like the Twitter graph, who follows whom. That would be a directed social network. As far as the semantics, for our purposes, we want to think of an edge from V to W as meaning that V has some influence over W. Okay? So when V updates its opinion or its action, there's some chance that will cascade to W updating its opinion or action. Okay? All right. So now I'm going to propose just a very simple model of how ideas, videos that are being shared, memes, whatever, how they might spread through a network. Okay? There's many other such models as well, but this one I'll do fine for our purposes today. Okay? So imagine that some vertex is active. So another thing which is sort of amusing, all this stuff, this idea of like looking at spread in networks, this has been around since before computer science, right? People cared about this before computer science was really a discipline. Epidemiology, they cared a lot about the spread of stuff through networks, okay? And that's actually where these models come from. They were looking at the spread of diseases and thinking about, who to vaccinate, who was it really important that doesn't get infected, because if they get infected, it's likely to spread to lots of other people. Okay, so that's where all this comes from. All right, so I'm going to say active instead of infected. It sounds a little better, a little more positive. So when V becomes active, it has an opportunity to activate all of the vertices that it influences. So we look at all of the edges going out of V, and for each of those vertices on the other side of that edge, there's some chance it now becomes active as well. So for all outgoing edges, with probability P, P is just some parameter of the model. Okay, think of it as like, 0.2, for example. So with probability P, W gets activated. If it's not active already. Okay? So for example, maybe V is activated. So now all of a sudden there's a chance for each of these 3 nodes to be active. Okay? And we flip an independent coin for each of the edges. So maybe this one actually, this person is influenced. Okay, they change their opinion, or they sort of do some product switch or whatever. Maybe this person is not activated, but this person is. So now in the cascade model, now these 2 newly infected nodes also have an opportunity to infect people outside of their outgoing edges. So for example, maybe this vertex fails to activate this vertex X, but this vertex at the bottom has a second chance, another chance to activate X, and maybe in that case it succeeds. And so then here, X does wind up being active at the end of the cascade, okay? So if you think about it, one way to think about this is, suppose V gets activated, when is X going to also get activated? It's going to be if and only if there's a directed path from V to X of edges that all got activated. Okay, so a path of the pink edges. That's exactly when X gets activated given that V was. Okay. All right, so a couple of things to notice. So in this model, again, there's lots of variations, but once a vertex is active, it's active forevermore, okay, first of all. And then second of all, notice that, it's sort of memoryless from a vertex's perspective, right? So if you find out, that somebody really likes, some new song, the first time maybe you ignore it, the second time maybe you ignore it, the third time maybe you sort of, listen to the song yourself, okay? But it's assumed to be independent, right? So each of those sort of times you see a friend of yours listening to a song, you have an equal independent probability of listening to it yourself. So any questions about the model? So this is just a model you could posit. So you can imagine doing lots of things. You can imagine doing simulations to see who gets infected as a function of who starts the cascade. So what people have really been focusing on the optimization side is how do you get this process to spread as far and wide as possible. Okay, so people are sort of thinking it's like, oh well, we have some marketing budget, or we have a sort of limited number of free products we can give people, I have there's 10 people I can take the time to call them on the phone and try to convince them of some new idea, and then the hope is that the cascade will take care of the rest. Okay, so you have a small investment up front, and you're relying on this cascade to spread your ideas or spread your product or whatever far and wide. And so the question is, what's the best way to do that? And so the objective could be to compute the k most influential nodes. That is, you want to maximize over all subsets of size k, f of s defined as the expected, remember it's a random process, okay? Remember you flip a coin for each edge. So that's why there's an expectation. So the expected number of active nodes at the end of the cascade if all of the nodes of S are active at the beginning. Okay? So certainly this is always going to be at least k, right? So if you activate k people at the beginning and it never spreads anywhere, you're going to have exactly k people be active. The hope is that maybe it goes from this seed set of size k via the cascade to a much, much, much bigger set of people. Okay? And so if there's some magical set of influential people where that's likely to happen, you want to figure out who they are. Okay? So that's the influence maximization problem. So let me just tell you the punchline, because we're out of time. So it's natural to think of a greedy algorithm for this, actually. So currently you have nobody, right? You haven't called anyone on the phone to tell them your idea. And so who do you call first? Well, you call the person that's going to lead to the biggest jump in the objective function value. Okay? How do you decide on the second person? Well, you say, well, let's look at the person who gives us the biggest jump relative to where we already are. Okay, so maybe on average, it's going to reach 12 people with this first person, and then the second person, I'll reach 20, so 8 new people compared to just having the first person. And so you can just do that k times, and that's the greedy algorithm. And it turns out exactly the same analysis that I showed you for max coverage applies to this and a bunch of other problems as well. Okay? And the basic reason is that if you think of the process in this sense, where basically you're just flipping coins for all of the edges, and the question is just how many vertices are there paths to, if you think about it, you realize that after you've flipped the coins for all of the edges, this is actually literally a coverage problem, where the sets correspond to who can be reached from some vertex. So if some vertex has paths to 20 different vertices, that's going to correspond to the cardinality of the set. Maximizing the number of people that you actually reach is exactly the same as the coverage problem with those definitions of subsets. And then the influence maximization problem, the only extra bells and whistles is that there's an expectation. So it's not one coverage problem, it's really kind of a superposition, an average of a bunch of different coverage problems. But if you stare at the analysis I gave you for a little bit, you realize it still works just fine. Okay, so again, 1 minus 1 over E. So Thursday will be a traveling salesman problem. See you then.